I tested whether neural networks can think in loops, 26 experiments, 236 training runs. The answer surprised me. 2 ideas. First, a spatiotemporal canvas, a 3D grid where different regions handle different modalities. Video, actions, proprioception, reward, multi-encoder, multi-decoder. That's where the omni-modality comes from. Second, loop detention. The same transformer blocks iterate multiple times per forward pass. Not to do different things, to think longer. Standard fine-tuning forces the model to commit in one pass. Looping gives it more compute to refine before committing. 3 hypotheses. 1. Looping enables iterative reasoning. 2. The shared canvas creates multi-modal binding. 3. Token allocation follows cortical magnification laws.
Here is how the looped block works. Take a standard transformer block. Run it L times instead of once. At each iteration, add a learned loop embedding. A sigmoid gate controls how much of each iteration's output to keep. 0 initialized embeddings mean the model starts as an identity function over the pre-trained weights. No distribution shift. Safe to graft onto any frozen backbone. For CogVideo X2B, we wrap all 30 DIT blocks. The frozen backbone contributes 1.69 billion parameters. The trainable loop embeddings and gates, 350,000. That is 0.02% of the model.
This is canvas engineering in practice. 3 examples. First, a robot manipulation canvas. 5 time steps, 8 by 8 spatial grid. Visual patches get 56%. Actions get 2%. Proprioception and reward fill the rest. You define it in 10 lines of Python. Second, a computer use agent. 16 time steps, 32 by 32 grid. 16,000 positions. Screen pixels dominate at 56%. Mouse and keyboard get less than 1% each, and an LLM steering channel for high-level goals. Third, multi-robot control. 2 robots share a canvas. Each gets its own camera and action region. A shared task region lets them coordinate. The layout defines who sees what and who controls what. Canvas engineering is how you give a video diffusion model omni-modal I/O. Experiment 6. The strongest result in the entire project. A 3-block for-loop model, 1.49 million parameters, versus a 12-block single-pass model at the same parameter count. The looped model wins by 1.73x on total loss. P less than 0.001. 5 seeds. Replicated. This is real. Looping gives you the representational power of 4 times the depth at 1/3 the parameters.
The mechanism is fixed-point convergence. Cosine similarity between consecutive loop representations increases monotonically, 0.926, 0.973, 0.990, 0.996. By 8 loops, 0.999. The model converges toward a fixed point of the weight matrix. This is deep equilibrium model dynamics. The practical benefit is implicit regularization. Contractive mappings reduce overfitting and create smoother optimization landscapes.
But does it reason? I tested this 3 times. Experiment 2. Multi-hop reasoning. If looping enables iterative reasoning, harder tasks should benefit more. Instead, the benefit decreases with difficulty. 1 hop, 2.35x, 3 hop, 1.59x, the opposite of the prediction. Experiment 21. Collision prediction. 4 conditions, baseline, looped, depth matched, parameter matched, all achieve identical performance. T-stats all below 1.5. All not significant. Experiment 22. Morphology times loops. A 2 by 3 factorial. 30 runs. Loops help action prediction 1.06x, p less than 0.0001. But the interaction with morphology is dead null. T equals 0.04, p equals 0.97. Loops help identically with or without body description tokens. The iterative reasoning hypothesis is falsified.
Experiment 24 tests multi-modal binding, jointly predicting observations and actions on a shared canvas. The result, all joint conditions degrade action quality by 19%, p less than 0.0001. The number of observation queries does not matter. 2 queries hurts as much as 32. The damage comes from gradient interference between observation and action losses in the shared representation.
The capstone experiment, CogVideo X2B, 1.69 billion parameters, RealBridge V2 robot video, 480 by 720, 7-dimensional actions, 12 conditions, 4 loop counts times 3 freeze levels, 36 training runs, $152 of compute on Lambda A100 GPUs. The result, 3 loops is consistently optimal at every single freeze level. Frozen, 1.66x over 1 loop. Unfrozen, 1.23x. Half frozen, 1.08x. And the frozen 3-loop condition, with only 350,000 trainable parameters, achieves lower action loss than every unfrozen condition with 33 times more parameters. The ANOVA is globally null, loops p equals 0.2, freeze p equals 0.72, but the effect sizes are large. Cohen's d up to 2.8. The experiment is underpowered at n equals 3. The pattern is consistent, but needs more seeds for definitive evidence.
So what is looped attention actually doing? 3 things. First, parameter-efficient depth via weight sharing, 1.73x advantage, replicated and significant. Second, implicit regularization through contraction toward a fixed point, 3 times lower variance across seeds. Third, spatial compute allocation when per-token gates are used, 1.24x visual loss improvement. What it is not. Iterative reasoning. 3 independent experiments falsified that claim. The looping gives you better representations through regularization. The omni-modal capability, the doing things part that comes from the canvas architecture, the multi-encoder, multi-decoder design, 2 separate contributions, both useful, for different reasons.
4 recommendations. 1. Use 3 loops, consistently optimal across scales from 1.5 million to 1.69 billion parameters. 2. Freeze the backbone. For action prediction, unfreezing 100 times more parameters gives 0 benefit. 3. Upgrade the action decoder. The 183-parameter action head is the bottleneck, not the backbone. 4. Do not use naive multimodal loss. We open-sourced Canvas Engine, a Python library for grafting looped attention onto any video diffusion model. 10 lines of code to get started. 26 experiments, 3 definitive negatives, 1 strong positive. Paper and code are open source.
Built-in collaboration, designed, analyzed, and written together. Links in the description.